Bismillah ar-Rahman ar-Rahim. After finishing the kinematics of rotation, we need now to discuss the dynamics of rotation. We apply a force on an object to make it rotating. Let me show you this object which is rotating. It is like the door, okay, of your classroom or your house, okay. Let me apply a fixed force. I have a constant force. Let me assume it is 10 newtons. I can apply 10 newtons on this door, for example, to make it rotating, wishing it will rotate. I apply 10 newton here, okay. Does it rotate? Doesn't rotate. Okay. If I apply the 10 newton here, at this point, it is the same 10 newton. It is rotating, but it is difficult to rotate the object, okay. Now, if I apply the 10 newton here, at the very far from the axis of rotation, you can see it's very easy to rotate. Also, you can think of applying the 10 newton. It is the same 10 newton here. Does it rotate? Doesn't rotate. It will never rotate. Or even a pull. If I pull it with 10 newton, does it rotate? It doesn't rotate. So we have to be careful. Dynamics of rotation is not the same as the dynamics of linear motion or translational motion, okay? There we said F net equals MA. The force by itself was more than enough for us. But now the force by itself or the force alone is giving me different dynamics of rotation of my object. So we have to define a new physical quantity, okay? To take care of these different results of the application of the force. You got my point? The force alone cannot show me the dynamics or the correct dynamics of rotation. But what is this new concept? It is called the torque, okay? So rather than talking about the force, we'll talk about the torque. What is this torque? Its symbol, the symbol used for torque is tau, okay? And it is a vector quantity similar to the force. The force was a vector quantity for translational motion. Here, the torque, which is the analog for the force, will be also a vector quantity. So equals, it is defined as R cross product with the force. Okay? What is this R? Because we know the force, but what is this R? R is the position vector, okay? From where should we draw this position vector? From the axis of rotation. So we start our position vector from the axis of rotation. And what is the end of it? We draw it from the axis of rotation to where? To the point of application of the force. The point where we apply the force, the point of application of the force. Let me show it in this diagram. I have an object. You see, this is my object, which is the orange rigid body. This is the axis of rotation, so it is pivoted. We fix it at this point, this axis of rotation, and we apply a certain force F. So this is the point of application of the force. We apply the force here, okay? And this is the axis of rotation. So from the axis of rotation to the point of application of the force, we draw the position vector. So this is the position vector R. And this is the force, okay? So we need to make the cross product, and we have studied the cross product thoroughly earlier in this course, okay? So this torque is a vector quantity, as you can see. Torque is a vector quantity, okay, meaning that it has magnitude and it has a direction, okay, magnitude and direction. Also, it has units, as you can see. Unit of a position vector. Position means meter, and force, which is Newton, so it has units of Newton meter. Okay? Let me elaborate more on the magnitude. What is the magnitude for a cross product, which we studied before? The magnitude will be torque magnitude equals the magnitude of the position vector, okay, multiplied by the magnitude of the force, okay, multiplied by sine the angle between these two vectors. Okay, so this is R, that is the force. We extend R, and this is the angle between the two vectors. Okay, it is the smaller angle between them, or the small angle between them. Don't take the large angle. Okay, so R magnitude, force magnitude multiplied by sine phi. We can rewrite this if we take the force sine phi. If you look here in this figure, you take the force, analyze it into two components. I can analyze it in a component with this R. So we call it FR, this component. We call it FR, or the radial component of the force along the position vector, FR. Because this angle phi, so this will be the neighboring or the adjacent, it is F cosine phi. Okay? And the other component, this one, which is opposite to phi, so this will be F tangential, Ft. We call it Ft because it is tangential to the rotational motion of this point. Okay? So it is tangential to the circular path. F tangential will be F sine phi. Okay? So I can take this F sine phi and replace it with F tangential. So I can write this as R, the magnitude of R, the position vector, multiplied by F tangential. But what is F tangential? It is F sine phi. So I take F sine phi, replace it with F tangential. Another way to look at this problem to find the magnitude of the torque, to take the sine phi with the vector R, the magnitude of the vector R. So this is the R vector, this angle phi, okay, they are opposite. They share the same head, so this phi is this phi. So I can analyze the position vector into two components. One component perpendicular to the extension of the force, okay, and this will be R sine phi. It is opposite to phi. And another one, another component, which is parallel in the same direction as the force, we call it R parallel, that is R cosine phi, because it is neighboring to phi. Here it is opposite to phi. So what is R sine phi? It is the perpendicular component of the R. So this is nothing but R perpendicular multiplied by the magnitude of the force. Okay? Okay? And it is given the name, this R perpendicular, we call it in the book, it is moment arm. Okay? Which is the component of the position vector which is perpendicular to the force. We call it the moment arm. Okay. So this is how to calculate the magnitude of the torque. What about the direction of the torque? The torque can be positive, it is a vector quantity, can be positive, can be negative. So we will use the terminology which we used earlier for omega, the angular velocity, and also which we used for alpha, which is the angular acceleration. Use the right-hand rule, okay? If the motion, in this case, the torque is causing counterclockwise motion, so the torque will be out of the plane, so it is positive, okay? If this force was a little bit like this, it will cause rotation, which is clockwise. So you put your fingers, okay, with the direction of the force or of this multiplication of cross product of R and F. So R cross F will give you something outward, which is positive. Okay, so it will be positive if the resulting torque is outward, or if it causes clockwise, counterclockwise motion. If the resultant torque causes counterclockwise rotation or counterclockwise acceleration, as we'll see later on, it will be positive. But it will be negative if it is inward. Inward. What do we mean by inward? If this is my axis of rotation, this is my R vector, and this is my force. Okay, so you use the right hand rule. R cross F will give you inward. So this inward will result in negative torque, or as you can see, this product give me clockwise torque or clockwise rotation, so it will be negative. Okay, the same terminology which we used for omega and we used for alpha. Okay, I think now it is time to get an example to find what is the torque. So if you have a single force, the torque will be R cross F. If you have more than one force, okay, for more than one force, we should talk about torque net, okay, and we add the torque of the first force, torque number 1, plus the torque of the second force, okay, vector sum. Some of them will be positive and some of them will be negative according to this agreement which we agreed earlier. You just add them. Some of them will be positive if the torque is outward, or negative if the torque is inward. Let me take a simple example to explain this. Well, I'll have example related to this meter stick, okay? And the meter stick, we will pin it or pivot it. Pivot means the point which is fixed and our object is rotating around it, okay? So here I'll have the meter stick. It is fixed at a point 20 centimeters from it is a meter stick. So when you see in the question, meter stick means that the length is 1 meter exactly. Okay, so this is 20 centimeters from the edge. Okay, and we apply different forces. I'll show it on the graph in a minute. You can see it here, my son. So my object is rotating in a horizontal plane. So it is horizontal plane rotating like this. Okay, so the gravitational force is not doing any work or torque. It doesn't affect the motion here, and it is frictionless. And I am applying several forces. Okay, so we'd like to find the torque net. Example: you have a thin meter stick fixed at 20 centimeter mark, okay, from the edge, and there are several forces acting on it. Okay, so this is my meter stick. It is pivoted here at this point, so this is my pivot. Pivot means the axis of rotation. It is fixed. Okay, so I have, this is the meter stick, pivoted at 20 centimeter. It is meter stick. The length is 1 meter. And in this case, we have how many forces? 5 forces. All forces are equal in magnitude, which is 10 Newton, but they have different directions and different position vectors relative to the pivot point. And the question is, find the net torque of these forces, these 5 forces, about the pivot. So this is the pivot, and would like to find the total or the net torque. As you can see, torque net will be the vector sum torque number 1 plus torque of force number 2 plus torque of force number 3 number 4, and number 5. And be careful, all of these are vectors. Let us see. Here, for the torque number 1, I have the force. So this is R1, as you can see. This is R1. Okay? So R1 cross F1, I have outward torque. So it is positive. Okay? Or you can think of it another way. This is the pivot, and this force is trying to rotate the stick in which direction? In the counterclockwise direction. So it is positive because counterclockwise. So what is the magnitude? So we know it is positive, but what is the magnitude? It is R, okay, multiplied by the magnitude of the force, multiplied by sine the angle between them. And the angle is 90, so sine 90 is 1. So the distance R is 0.2, because this is 20 centimeters, multiplied by the magnitude of the force, which is 10 newtons, multiplied by sine 90, which is 1. Okay, I am done with this one. F2 is exactly acting at the pivot. So what is the R here? What is the R? Correct. Your guess is correct. It is equal to 0, because the force is exactly acting at the pivot point. So R is equal to 0. So this is plus 0. R is 0 multiplied by the force, which is 10 multiplied. So this is 0. Okay, because R is 0. Plus or minus. Let me check. Now, for F3, the force number 3, this is the pivot. Force number 3 is trying to rotate the object clockwise. Okay, so it should be negative. So this will be negative. Another way, where is R3? This is R3. Okay, R3, use the right hand rule. R3 cross product with F3 will give you inward torque. So the inward is negative. How much is this? It will be R3. How much is the magnitude of R3? It is 0.2, because 20 centimeters from this point, which is 20 centimeters and 40, multiplied by the force, which is 10 newtons, multiplied by the angle. So the angle here is 90, so this will be sine 90, which is 1. Similarly, F4. F4 is causing also a clockwise rotation, so it will be negative again. Negative. And this will be R, which is 0.2, multiplied by the force, which is 10, multiplied by sine the angle between R and F4. So R4, which is the same as R3, it will be 0.2. And this is F4. So what is the angle? Angle is this one. So this is 60. This will be 30. Okay? So it will be sine 30. So this is R. This is F4. And the angle between them is 30. Because this is 60. So this will be 30. Finally, I am left with torque number 5. I have, this is R number 5. Okay, so R5, the position vector of this force, as you can see, the angle between R5 and F5 is 0. Okay, so this will be plus, now the distance from here to there, this is 80 centimeters, so this is 0.8, multiplied by the force, which is 10 newtons, multiplied by sine 0. But what is sine 0? Is 0, so this term is 0. Similar to this term, which is 0. So I have this term 0, and this term is 0. This is 0 because the position vector is 0. We apply the force at the pivot. And this term is 0 because the angle between the force and the position vector is 0. So sine 0 will give me 0. So let me add these numbers. So this will be 0.2 multiplied by 10. So this is 2 minus... this also will be 2 minus 0.2 multiplied by 10. So this will be 2 multiplied by sine 30, which is 1/2. Okay, I am left with, this will cancel that, and I am left with minus 1 Newton meter. This is the torque net. Okay, so the torque net has a magnitude of 1 Newton meter. What is this minus sign? What is this minus sign? Okay, it tells the direction of the torque net. The torque net is negative, so it causes clockwise rotation. Okay? So if this stick was at rest and we apply all of these forces, you will see it at the end rotating in the clockwise direction. Okay? Or if we apply the right-hand rule, okay, clockwise rotation means that my torque is inward, and the inward is the negative. So with this example, I hope you understand the concept of the torque. Thank you.